Thank you, Lil, for a very nice introduction, and thank you for your invitation also from the Whole Energy Institute here. Texas A&M is a place I really love to visit. This is my first time. I'm amazed by how big the campus is, very distributed, a gigantic operation right here. So today, let me share with you this topic I've been working on for the past 18 years as a faculty member at Stanford. I joined Stanford in 2005. At the time, the battery was not hot at all. So people ask you, why do you want to work on batteries all the time? There's no way I could get funding, no research funding available. It was very interesting time, but nowadays you see it just completely changed. For the reason very clear of driving the batteries application is consumer electronics, electric transportation, including vehicles and even electric planes, and also stationary storage as well. I'm showing right here these two areas adding together is gigantic market. For many of you looking on electrical grids, you all know stationary storage is so important, more and more important. Right now to integrate solar and wind and other renewable electricities. Then we come back to ask these fundamental questions. So store energy in a way is storing electrons. How do you do that? Is the battery technology the right fit? And in this storing energy, storing electrons, the electron has negative charge. You need to balance that, but this simple chemistry with a positive charge, that's ions, cations, and not only that, oftentimes electrons and atoms need to store inside of materials that we call a host. This host materials define the potential voltage where the electron will be sitting at. That's how you build out the batteries. And N plus is so much heavier than electron, and host is so much more heavier. So this, I will call it, this is gigantic overhead to store electrons. So you want to minimize overhead. The first thing you need to do is I want to use the lightest weight, as light as possible. Lightest weight is proton. If you use proton, that's fuel cells. If you use lithium, that's lithium-ion battery. If you use sodium, that's sodium-ion. If you do magnesium, that's magnesium. If you use lead, that's lead-acid batteries. It's as simple as that, right? You want to use lightweight. You also care about how high the voltage you can access. This is related to electronegativity or positivity of the element N. Lithium gives you the highest voltage on the top, right here. That's why consuming electronics, no surprise, you got to use lithium. You need to have high enough voltage to drive your devices. I mean, if you use you can use voltage jumper, but it's just not as convenient as starting from higher voltage. Proton will get you about 1.5. If it's water, it's 1.23. Thermodynamics, a stable potential. And then the cost also coming in. Used to be lithium-ion, you don't care about lithium cost. Now with so many lithium-ion batteries, you do need to care about lithium cost. However, the cost is still only about 10% or less the total battery's cost. So these are the considerations. It's very easy for you to see. You want to pick light element that's lithium. You want to have high voltage that's lithium. You don't want to have too high cost. So far, lithium cost is not too high yet. So lithium has been dominating. 2019, Nobel Prize in Chemistry was given to the development of lithium-ion batteries. It's very, very useful. These are based on this set of materials, graphite, to integrate lithium in and out. Graphite is exposed, electrons coming in and out. Lithium copper oxide, lithium manganese oxide, lithium phosphate. Through the mechanism called intercalation chemistry. You have a housing material, it doesn't change that much. It's intercalate lithium, you bring in an electron, take out lithium, you take out electrons. That's the basis for the Nobel Prize winning work. Then you ask, what's next? What are the grand challenges for batteries to enable even provide the deployment of electric transportation, grid-scale storage? And you ask the questions, can energy density go higher? We are currently sitting at roughly 250 watt-hour per kilogram. Can we go to 500, double? Can we go to 1,000, 4 times? That changed the whole game of mobility. You can have electric flight, domestic flight, certainly possible. Battery life to 30,000 cycles instead of about 3,000. You need 10 times longer life. Maybe if you do lithium-ion phosphate, you can go to 5,000, but you still need to get 6 times more. 30 years. I mean, lithium battery on your phone. How long would you be able to feel, the decay of the capacity? Within 3 years, you feel the decay already. If people are teaching you as lithium might last for 15 years, I don't trust that. Your own experience already telling you, no, it cannot last for so long. But can you go for 30 years? Can you do fast charging within 10 minutes? Can you make the battery safe? They're using organic electrolyte, having a campfire, particularly when you use for grid-scale energy storage. The system is so big and it's dangerous. The cell cost, can you go down to $10 per kilowatt hour, which is about 10 times less compared to the current cost? Can you do that? What about the materials availability and circularity? To go to gigaton level, these allow you to go to terawatt, hundreds of terawatt level of storage. That's what it takes to completely decarbonize electrical transportation. That's what it takes to really have the electrical grid to be completely clean. We need to have that. So these are the questions we try to address. My lab, we have been working on this over close to 20 years now. High energy density batteries, fast charging, safety, new type of aqueous chemistry, develop new tools, and so on. But let me share with you now, come back to the topic of energy density. How high can we go? We've been doing that for really 18 years. Can we get to 500 or 1,000 watt per kilogram? So my lab has been early day pioneer the development of silicon anodes and lithium metal anode and sulfur cathode, also phosphorus anode as well. These offer you about 10x of charge storage capacity compared to current technology. Can potentially double or go to 4 times of the energy density. It's shift from intercalation mechanism to alloy mechanism, plating and stripping mechanism, and conversion reaction mechanism. Completely different from before the Nobel Prize winning work back in 2019. So the challenge we are facing with the new materials, this plot is the vertical axis is relative volume change versus the amount of lithium you store. This is the lithium versus the host atomic ratio. The higher the number, the more energy you are going to store. But the more lithium you're putting in, and the relative volume exchange will go up tremendously. Traditional materials, the Nobel winning prize works less than 10% volume change only less than 10%. But new materials coming in often need you to see the volume changes a few 100%. So it's much more volume change right there. Not only that, if you look into deeper, the new materials on the right, they are not stable. You put lithium in and out, you break the chemical bonding of that host materials. You move the host atoms to very long distance on the right. You cause complete structure change, because gigantic volume expansion. And we really need to redesign the batteries and in a very, very different way, from materials and chemistry level all the way to the whole system level. That has been the topic my lab trying to tackle in the past close to 20 years. But if you could do that, this is the pathway. Graphite MMC combination is 250, now maybe close to 300 watt per kilo. Silicon anode coming in with MMC get to 400, might be even 500. Metallic lithium MMC, that's 500. This is famous battery 500 consortium. We try to get to 500 while the Tello, I serve as co-director of the consortium. Lithium metal and sulfur can potentially get to 600 or 1,000 while Tello. But you're facing this gigantic volume change using silicon as an example. Silicon, one silicon atom store 4.4 lithium. 6 graphite, 6 carbon atom only store 1 lithium. So silicon is 4,200 million multiplier. But the volume expansion is 4 times. It's gigantic. It causes materials breaking. It causes instability of the interface between this particle and organic electrolyte. Because volume expansion happening when lithium coming in, once you discharge, lithium going out, it shrink. It's never stable interface right there. So this interfacial structure will never be stable. This is a killer to the batteries. I still remember when we published the first paper at the end of 2007, December, I mean, officially comes out in 2008, January. This is the landmark paper in the battery field. How do we use nanoscience design to overcome volume expansion problem? In this case, is silicon nanowire flow directly onto a metallic current collector. Lithium can coming in and going out from the sidewall of this nanowire. This nanowire is connected electronically and also mechanically with underlying metallic foil. So this wire's diameter is small enough to relax the strain without breaking. Chemistry was my first graduate student actually working with me on this. So after this paper, it really opened up the whole research field of nanoscience for battery research. And to understand deeper, together with my colleague, Professor Bill Nix, my earlier student, Matt McDowell, now Italian faculty member in Georgia Tech, we developed a tool of in situ transmission electron microscopy. Inside this holder, we can mount these nanowires onto a GoPro and insert it into ionic liquid. And with lithium cobalt oxide as cathode, we are building a single nanowire battery inside transmission electron microscope. Using this technique, we could really look at the when we charge, for example, this nanowire surface coated with copper, and you can see gigantic volume expansion taking place. The scale by light is 200 nanometers. The surface coating of copper is broken, but nanowire survive without broken. If you go look at the particle, one question is, what's the critical breaking size below which it doesn't break, above which it will break? So we want to figure out this critical breaking size. In the middle of the screen, that big particle is 800 nanometer to start with. Now lithium coming in and make lithium with silicon become alloy, amorphous alloy. You see this crystalline core keep shrinking. These particles, it just keep expanding until the stress is so big, and then it cannot take anymore. You see this particle is broken. Once it's broken, this material is no longer connect with each other, so your battery's capacity will just decay so fast. The first cycle, you build a battery, you charge it up, and the battery's already died. We use a tool like this to figure out what's the critical breaking size for a diameter spherical shaped particle. It needs to go down below 150 nanometer in diameter to minimize breaking. If it's too big, it's going to break. So this has been providing a guideline for the whole industry to use. You know, what are the critical breaking sizes industry needs to pay attention to in order to avoid breaking. So my lab has been through this 12 generational design, avoid breaking. How do you build stable interface? I won't go into detail of that. In 2008, we published the first paper. I founded my first company, Amprius. Really, after the Silicon Valley's venture capital talking to me many times, so I decided to do it. In 2008, Empress was formed. Empress is now delivering 450 watt per kilogram of product to the market. And we also have silicon particle line that's delivered 350 watt per kilo. This is so much high energy density compared to the existing graphite technology. So one of our batteries, high energy density one, we supply to Airbus, the Cypress S, this commercial drone, flying in a very high elevation, about 60, 70,000 thousand feet height, continuously for 25 days without, they don't need to come down to the earth. They have a solar cell to charge it up during the day and store inside into our high energy density battery, and flying most of the time rely on the battery power. This requires very high energy density, only Empress can make it successful. So we also demonstrate silicon can do fast charging, much faster than graphite. Graphite cannot. 6 minutes to 80%. This is a huge breakthrough right there as fast charging, in addition to high energy density. The reason is silicon, once you put lithium in, it becomes amorphous. Three-dimensional structure lithium can come in. Not only that, its potential is slightly above graphite. This provides a safety margin of this voltage. If you do fast charging, silicon's potential does not go down to the lithium metallic lithium plating potential, make it very safe. So silicon could do that. So we have been actually developing the product through Empress. And so last year, the company went for public, September 22nd. It's just about 1 year. So last Friday is 1 year anniversary. So I was so excited to see the company went for public, now having more resources to expand the manufacturing. So for the high energy density battery, so what's next? Is we need to work on metallic lithium anode. Metallic lithium anode has no host. It's based on metallic lithium foil plating and stripping. Very different mechanism for intercalation. If you take metallic foil lithium, it will form this SEI layer, solid electron interface, right? To put into organic electrolyte. And then once you charge up the batteries, you're going to plate the lithium, cause the thickness change. There's no guarantee it's layer by layer, very flat plating, because the surface curvature change, topology change, cause the cracking of the solid electron interface SEI. This crack is your hot spot. Lithium really like to go in and deposit there fast. There's nothing block that, right? You pick up the electron and deposit, and then you can form this metallic lithium dendrite. And this dendrite can cause the battery shorting, catch fires. So this is very bad. Actually, most of the battery can catch fire is due to the dendrite plating. Even you don't use metallic lithium as anode, you use graphite. But with time, when you use your battery over and over, this starts to happen, particularly at the fast charging condition. Once you strip lithium, you might strip from the bottom of this dendrite, causing this isolated lithium formation. You are losing lithium, metallic lithium. You lose your capacity very fast. And before long, your battery will die. This lithium plating for practical cell installation, we need 3 milliamp hour, centimeter square oftentimes, or 5 milliamp hour. That's 15 micron of lithium for one layer of the electrode. So when you do plating, you plate 15 micron. When you do stripping, you strip away 15 micron. Your batteries consist of multi-layer of the electrode. This battery cell is going crazy. Deposition will expand. When you do discharge, it's going to shrink. The lithium metal cell cannot handle that. So there's so many problems coupled together. And when the standard formation cause shorting and all these surrounding phenomena, what I truly believe is if you want to solve the problem, you've got to identify the root causes. And the middle two are the root causes. One is doing plating and stripping. this volume fluctuation is too big. The second is metallic lithium is so reactive chemically with nearly everything, right? So these two things adding together make it so hard to handle. So 2017, we published this Nature Nanotech perspective article. This is very highly cited, probably close to 4,000, 5,000 citations right now. And to really show with the whole world, how do we solve the problem? We need to address the root causes. So in order to address the volume fluctuation problem, in 2016, we published a few papers in 2016, particularly when Steve Chu come back to Stanford in 2013. After stepping down as the Secretary of Energy position, he come back to Stanford. He and I start to work together. We brainstorm, and they say, well, we got to solve the lithium metal problem. That's the most important, one of the most important problems we need to work on. So we published a concept of stable host by designing this hollow carbon and deposit lithium inside the hollow host and hosting and guiding the lithium deposition. I'm going to tell you in a little bit more. And then we have been through a whole series host design, so I don't need to bother you because I need to go deeper. And then, and also in parallel, we understand the interface needs to be very stable. The metallic lithium with organic electrolyte. We need new type of organic electrolyte. Working with Professor Zhenan Bao in Jianqing, Zhenan and I already have more than a decade of collaboration to design battery material, particularly organic materials. We have breakthroughs in the last couple of years in designing new type of organic solvent and to stabilize that interface. And the third thing we also need, not only the materials and interface, we need to also really need to understand what happened. So my lab over the last several years have been developing new tools, characterization tools, for example, cryogenic electron microscopy, ultramicro electron technique, and potentiometry measurement, and to understand what happened down to atomic scale resolution, to understand the thermodynamic parameters, gives free energy oscillation and entropy, and so on, and kinetics information. So these all added together to contribute to our understanding. Now let me share with you some of our findings. The first question we ask is, when you deposit lithium and strip lithium, how does the deposition happen? Particularly right at the beginning. How does that happen? It was not understood at all. So in 2017, we look at this problem deeper. You take lithium and electron, deposit forming metallic lithium. You're going to cross the energy barrier right there of particularly this nucleation event to deposit on different substrate. Classical nucleation theory is teaching us if you increase the driving force of nucleation and the size of the nuclei diameter becomes smaller, but the number density is a lot more. It's the scaling rule of radius versus the overall potential, the driving force of nucleation is 1 over eta. But the number density is the cubic function of eta. So, and looking at this, we were able to use different current density for deposition. The higher the current density, this number per centimeter square, is giving you more driving force. And we are finding that smaller driving force, you see this big nuclei, 50 micron scale bar, but once you go to 10 milliamp per centimeter square, you see this nuclear size becomes so much smaller. And then you can count it, you can measure. It fits just classical nucleation theory so nicely, the scaling law. And why this is important? Because this determines the size of lithium metal that will affect the battery performance later. So Alan, after finish, he already joined Tesla, right? He joined in really at the right time, by the way. When Tesla stock was so low, he joined in. Because within a couple of years, this guy become a millionaire. He's rich right now. He was joining in the time compared to it's like 10x difference in the stock price. So he doesn't want to come back. He doesn't need to work anymore. Then we also ask the question, because we use copper for as current collector, you deposit lithium. If you look at this carefully, you measure the potential and at a very low current density, you see a voltage dip, and then plating happens. This has 40 millivolt of over potential needed to drive lithium metal nucleation happen on copper. But once you change the substrate using gold as the substrate, it's different. Highlighted right here, this red circle, there's no voltage dip right there. Plating will just happen. So lithium metal plating onto gold has no over potential for nucleation. Very different behavior. But certainly there's upper voltage plateau right here. This nucleation is, lithium can go from the first alloy phase and then the second alloy phase. So we look at this problem deeper. Actually, the phase diagram is teaching us a lot. On the top right here is between copper and lithium. At the bottom is gold and lithium. You look at the right-hand side, between lithium and gold. On the most right-hand side, close to pure lithium, gold has solubility inside metallic lithium, solid state, forming solid solution. What happens is lithium has this ability. If you deposit lithium onto gold, it will form one of these alloy phase, another of these alloy phase, and then lithium dissolve gold away, make gold more and more look like lithium before lithium deposition happening. There's no over potential this way. However, for copper, copper has no solubility in lithium. Copper is FCC structure, lithium is BCC, different atomic distance. They don't like each other that much. There's nucleation area right there. So you need to have over potential. Not only that, we actually explain, we also discover based on the phase diagram, not only gold, we shift the voltage curve up, right? Silver is good, zinc is good, magnesium is good to help lithium plating without over potential right here. Actually, after this publication, Samsung borrowed this type of idea on the solid state battery. They put silver on. They published that famous paper several years ago for solid state batteries using silver to guide the uniform plating of metallic lithium. But you look at copper, there's over potential, all right there, nickel, and carbon has also some over potential right there. So, and based on this, we now can design on a copper substrate. We pattern this gold line, and then after deposition, you see lithium deposition only like to deposit onto where the gold is. They want to grow right there. So this is first time spatial. We can control during battery charging where lithium will go. And based on this idea, we actually design this hollow carbon with the gold as the seed and build the electron doing lithium deposition. Now lithium metal will deposit inside instead of outside. Now this hollow carbon sphere will isolate metallic lithium from the organic electrolyte. You can build stable solid electron interface. So we made this structure. Let me show you this each video right here. Each video technique is really powerful for us to understand. What you see is this hollow carbon, this gold seed inside, and then you deposit lithium electrochemically. You see gold get dissolved away. Once you strip lithium out, you are going to see in a second the gold nanoparticles will come back, the black dots. So this is really clearly show gold helps the nucleation deposition of metallic lithium. So and then we build the electrode, with the seed right there, it gets better. So not only that, we also design graphene oxide. I think I'm going to skip through this quickly and as the host to deposit lithium. So I'm hoping through this type of idea, eventually we could promote lithium metal charging, discharging, giving you much higher energy density without blowing the dendrite and doubling and even 4 times of the current technology in terms of energy density. So let me also share with you this question. People kind of ask this question. Actually, people think that isolated lithium, they're dead because during lithium stripping, those dendrites, they're disconnected from the substrate. I remember that. So, but we asked this question several years ago. Fang was my postdoc, now just joining faculty in Wisconsin. Are those isolated lithium really dead? We asked this question. Now, if you look at battery cathode and anode, with this isolated lithium wire there, they are not connected to the left or to the right. There's no electrical connection. And everybody thinks they are dead. I thought so for the past 20 years, but not until a couple of years ago, we asked this question again. Now, imagine once you do a charging process, you apply current between cathode and anode, and this ionic current inside the battery cell and the electrolyte. You're going to have electric field from cathode to anode inside this organic electron. Even though this isolated metallic lithium, they are not connected electrically, but because this electric field inside this battery cell is going to polarize metal. Metal can be polarized in a perfect sense, right? So this polarization will create an electric field against external electric field to make inside of the metal. We know inside metal there's no electric field in the steady state. So what happened is you're going to polarize right hand side with positive charge, left hand side with negative charge. Once you have positive charge right here, you're going to dissolve lithium atom to generate lithium ion and electron will move to the left. And electron will pick up lithium ion and deposit become metallic lithium, lithium zero. So what happened to here is right hand side dissolve away. Left hand side self-deposition. So it's a self-dissolution, self-deposition. This whole thing, the data will move to the right, from the screen. Will move to my right? So we'll move to this side during charging. During this charge, it's the opposite. This dendron will move towards this direction. Imagine if this dendron move long enough distance, it's going to touch the lithium metal anode, will be connected electrically. The dead lithium is alive. It's very interesting. This is hypothesis. Let me look at this. So, and we designed an experiment, pattern this metallic island in the middle between cathode and anode. You see at the beginning, this is golden color, the metallic lithium. After you do charging process outside, even though this metallic island, they're isolated, not connected with anything. You see now metallic lithium, the golden color accumulates to the left. The right hand side is become darker color because those lithium are gone. It's very interesting. This is a self-dissolution, self-deposition mechanism. During this charge process, move to the right, this metallic island of lithium. So we actually simulate this process during battery charging and discharging. What happened this isolated island? Isn't that very interesting? Is even though they're not connected electrically, they're isolated, but they respond to the outside current, left to right, right to left. The degree of response, of course, is very easy to understand. If your external current is very high, you drive very high current, you're going to cause larger voltage gradient inside the battery cell. This response is stronger. That's number one. The second one is if the dendron is very long, then the two ends, the voltage drop will be bigger. Then response is also stronger. The longer it is, the easier it is. The swing back and forth becomes more. So we kind of figured that out in this Nature paper. We built the batteries. I won't bother you with all these details. So what I want to show you is eventually you're going to get to here. They're connected to the anode. And then they're activated. You recover your battery capacity. It's just incredible. So the protocol we recommend to the whole battery field, electric transportation, when you finish your batteries charging, including your phone, you're welcome to go home to try this if your phone already decay capacity. When you finish the charging, you do a fast discharge for about a minute or 2 minutes. Fast discharge. You drive that current because fast discharge driving the dendron to connect with anode. So after we published this Nature paper, one of my friends in Beijing telling me, oh yeah, I own this the fleet of electrical bus during Beijing Olympics 2008. The capacity already decayed. After reading our publication, he asked his team, he said, let's do a fast discharge for 2 minutes. And then his capacity recovered by 15%. So really full using the fleet of the bus. And we proved this in our lab by using tiny cell, but in reality, the batteries, they also prove that. So this is very, very interesting. The dead lithium is alive, can be recovered, right? So now let me share with you with remaining time. For a long time, I wanted to have a tool. I can image the batteries. I can see the atoms, but not possible. Let me tell you why. This is the metallic lithium dendrite. As soon as you zoom in using electron microscope, you can see the electron beam will destroy this dendrite right away. Metallic lithium's melting point is 180 degrees Celsius roughly. Its melting point is very low. The bonding is very big. You're going to destroy this structure. Nobody sees atoms of lithium. Even the lithium-ion battery has been used for, commercially 30 years now. Since research in 1970 until now, close to 50 years. And nobody sees atomic scale resolution of metallic lithium. And to understand the interface, not possible, right? So 2017, actually, we published the first paper in Science. And we show we can borrow a technique in biology, structural biology, called cryogenic electron microscopy. And cryo-EM for structural biology won the Nobel Prize in 2017 because this technique has been solving protein structure and so on. 2017 is maybe the week after the Nobel Prize was announced, our paper come out. We actually was the first group developed cryo-EM technique for battery research. And we, deposit this metallic lithium anode onto TM3. We freeze it to liquid nitrogen without exposed to air. It's very, very cold. We freeze all the motion right there. You stabilize metallic lithium interface chemically, and without exposed to air, we develop this cryotransfer technique and put it into the TEM, transmission electron microscope. This is a cold finger. We put liquid nitrogen right here. So continuously freeze the sample close to liquid nitrogen temperature. Then we image under electron beam. Liquid nitrogen stabilize your sample. That's one important one. The second one is, and it's leveraging what structural biology has been developed, is the direct electron detector inside transmission electron microscope. Using very low dose image, we can image already without destroying the sample. So I have my two students working on this. Zhang is already a hot young superstar in UCLA. He joined the faculty several years ago. Do you notice I have two students with the same last name, Li? I kind of made fun of them. I said, to working on lithium, you guys need to have the right last name. Two lithium students who work on lithium to make it successful. This is atomic scale imaging for the first time on metallic lithium. And so when we submitted this paper, it got reviewed, I think maybe 4 rounds of review, 9 months. We submitted to 2016 December, accepted September 2017 next year, because people couldn't believe we can see atomic scale imaging of lithium metallic for the first time. I mean, after we published paper, then seeing atomic scale resolution of lithium metal is easy, but people couldn't believe it. We need to do a lot of experiments to convince the reviewer to say this is really metallic lithium, right? So then we also now saw for the first time on any anode surface you have this layer, SEI, solid electron interface, so important. When you're charging and discharging efficiency to be high, determined to very large level your safety performance and so on. Nobody understands the structure. There's a lot of debate. So we were able to image for the first time. This is the layer about 20 nanometer thick of solid electron interface. It consists of inorganic particles, lithium oxide, mostly embedded into this amorphous matrix. This is an carbonate electrolyte. As soon as you added a little bit of fluorinated FEC, and this whole structure changed. Now you have this beautiful layer on the top, that's all lithium oxide. Then you have this amorphous layer, mostly you have bilayer structure. So this actually resolved one of the disputes in the field for the past 30 years. It's called a mosaic structure or bilayer structure. It turned out to be both exist depending on your electrolyte. So we resolved that. So not only that, so last year we have this paper. We now figure out how do we freeze the batteries while the organic electrolyte is still in there. But you need to generate in a way. This organic electrolyte needs to be very thin, otherwise too thick, electron beam cannot go through. So we developed this blotting paper technique to learn from biologists to generate very thin film of liquid and then plunge freeze it for liquid nitrogen. So now we have this lithium dendrite, bottom right? Freeze inside organic electrolyte without crystallizing the organic electrolyte, maintain as amorphous phase. If your organic electrolyte is too thick, it's like top left, right? There is very mass, too thick. Electron beam, you cannot see anything. So let me share with you, we have made the discovery right here. This is in the electrolyte state. This is the SCI layer, 20 nanometer for this particular electrolyte. We could also dry up this electrolyte, and then you look at the SCI again. This is only 10 nanometer, same electrolyte on the lithium is SCI. This is telling you this interface is swollen with organic liquid electrolyte under the operation. The dry state is only half of the thickness. But then we compare different electrolyte recipe. These are all different solid molecules right there. And now plotting this in a way is the SCI swelling ratio is in the wet state thickness divided by the dry state. And the vertical axis is electrochemical parameter called Coulombic efficiency. The higher the better. Coulombic efficiency describing if I store 100 electrons during charging, how many can I get out? You want it to be 99.99%. Even losing 1% is not acceptable, right? So the lower the swelling ratio, the higher the Coulombic efficiency for this particular hero electrolyte we discovered between Zhenan Bao and me. And it's a very strong correlation. SCI swelling less will be better. And there's a really deep meaning in the chemistry. What happened? Less swelling means that interfacial layer has more inorganic component, more than organic. Organic was swelling, organic electrolyte. We have more inorganic. It's also due to this different solvent molecule. The first solvation shell structure is very different. And with a weakly solvate structure, it has more anion negative charge than the solid molecule. Then you build more inorganic in the SCI. So we kind of correlate this completely. So this is super exciting to me. So maybe last couple of minutes, then I'll stop. Right? I'll give you maybe just one example: long duration energy storage. Previously I was showing you the high energy density. So what about long duration? To integrate solar and wind electricity to the electrical grid, and we need to handle the power and the electricity grid, the fluctuation from minutes to minute, hour to hour, day to day, week to week, month to month, and even seasonal. Let's look at how big a battery you really need. If let's see, we want to store the electricity grid for 72 hours, only 72 hours. This is 200 kilowatt hour of batteries. This is gigantic. This alone is $20 trillion, roughly. And this takes 200 years to produce this type of batteries. And then the longer the duration, the lower the cost you will need this battery to be. So we are not there yet. Lithium ion is too far away. We need very long lifetime, right? Lithium ion is really not there. We need to maintain this free all the climate conditions, whether it's very hot or very cold. Lithium ion is certainly not there. We need to be very safe, cradle-to-cradle recyclability. So let me share with you 2018. Malami published his first paper. We asked ourselves, what's the longest life electrochemistry human being ever invented? very reliable, very safe. You want to very safe, you go to aqueous solution. Turn out to be this chemistry is cathode is nickel hydroxide become nickel oxide hydroxide as one of the choices. It's it can go very long charging discharging cycle, go 30 years. And then the anode side is hydrogen become gas, become water. Hydrogen gas become water back and forth. I actually use periodic table to come up with this chemistry myself. And then I write down the full cell equation. It's just a really nice balanced equation. I got so excited, I asked my postdoc, I said, let's work on it. But I didn't know this was already invented 40 years ago by using NASA and Hubble telescope for 30 years already. No problem free. The only thing is it's too expensive. Anything working in outer space, right? All very expensive. But anything working in outer space for 30 years is telling you very reliable. So I kind of reinvent this chemistry for nickel hydrogen gas batteries. But what I replace very expensive platinum with transition metal catalyst. Now make it very low cost, moving from outer space now for civilian use. So we show early days in my lab, 2018, this PNAS paper. This can just run 30,000 cycles easily. It's very reliable, just incredible chemistry, right? They're using water, using potassium hydroxide. And not only that, my lab also invented for the first time and said, hey, let me replace nickel. Can I use manganese, Mn? The cost is 10 times lower on lead or iron. We couldn't know how to make iron to work yet, but we made manganese and lead to work. Let me share with you the manganese version. We invented manganese hydrogen gas battery for the first time. 2+ become manganese dioxide during charging, proton and hydrogen coming back and forth, right? And we see this chemistry just run forever, really forever. So this is super exciting. So 3 years ago, I started another company called Reinventing to commercialize this technology. And this has very long cycle life, 0 accident, by the way. We passed the high safety standard, UL. And it never catch fire. You can shoot a bullet on it. You can throw it onto fire. It just never catch fire. And it can go down to -40 degrees Celsius and about 60 in Texas. I assume, this is perfect. So you don't need air conditioning, right? 0 maintenance. My God, this is just incredible. So we are delivering a product right now to the market. So, and this was a team several years ago. And it's super exciting to me. We just have about $2 billion purchase order coming in, another $6 billion in the pipeline. We are building up the gigafactory right now in Kentucky. We just raised another round of financing. So stay tuned. So this is super exciting to me. Now come back to the grand challenges. I was showing this high energy density. We're going to have very long life. I didn't have time to talk about fast charging. Also amazing science and engineering behind that as well. Complete safety. Our nickel hydrogen, we showed that increases solution chemistry. Cell cost not quite there yet, $10 per kilowatt hour. I'm just organizing a team of people, writing a big proposal to Department of Energy. So I really try to get to below $10 per kilowatt hour. Stay tuned. Materials availability is similarity as well. So my lab also it has been working on battery recycling, lithium extraction from ocean, from the brine, and so on. So we start. Let me end my talk by thanking the whole research group and DOE for the support, both EI and BES. Thank you very much for your attention.